So let's develop a little bit of computational knowledge here and how to deal with integrals of a handful of special functions using the definition. In exercise 5.3.63, we're going to consider a constant function, and we're told to show, using the definition, that's all we have at this stage, that the definite integral from a to b of constant c dx is c times b minus a. Well, first, constant functions are definitely continuous functions. So this function's continuous on the interval from a to b. So theorem 5.1 says continuous functions are integrable. So this is an integrable function, meaning we can consider any sequence of partitions which have a norm approaching 0, and the associated Riemann sums will have a limit that equals the value of the definite integral. Knowing integrability allows us to consider any appropriate partitions, that is, partitions for which the norm approaches 0. So let's use a regular partition. Let's take the partition x sub 0 through x sub n of the interval from a to b, where each of the little subintervals have width delta x sub k. Let's just denote it as delta x, and so they'll all be the same, b minus a over n. A regular partition, an equal width subintervals situation, as the book calls it. So we've taken the interval from a to b and busted it into n pieces of the same size. This is the size of the pieces, b minus a over n. We'll have, as we've seen in the past, x sub k will be the first x value plus k times the number of steps. X sub k is a plus k, b minus a over n. And c sub k is any element, or we could pick specific elements, knowing integrability. We'll have to do that in the future, but this one we'll just let c sub k be any element of the k subinterval. Now, the norm of the partition then is simply the width of all of the subintervals. Remember, the norm of the partition is the width of the smallest subinterval. Well, they're all the same width. We set it up that way. And that width is b minus a over n, so that must be the norm of the partition. So as n approaches infinity, we've got b minus a divided by n. That will approach 0. The norm of the partition will approach 0, and we're good to go. Knowing integrability, we can use this approach to evaluate the integral. So the integral from a to b of c dx is a limit as n approaches infinity, which is equivalent to the norm of the partition approaching 0, of Riemann sums. This is a sum from 1 to n of f of c sub k times delta x sub k. Remember, we took delta x sub k to be the constant b minus a over n. Now, I don't know specifically in this one what the c sub k are. In general, I'll need to know that, but hey, the function f is a constant function. So whatever you put into it, you just get the value c back out. So this one's a little special in that sense. So f of c sub k is c. That produces the limit of this Riemann sum. We've got a constant, c b minus a over n. There's no k's here. As k changes, this stays the same. So when we sum from 1 to n this constant, we simply get n times that constant. The n's will cancel, and we'll be left with c times b minus a. Take a limit as n approaches infinity. There are no n's in it. They canceled out. And you get c times b minus a, and we were supposed to get c times b minus a. So we now know how to integrate constant functions. Let's see, let's do several more of these. All right, let's look at a squaring function, a cubing function, and an example illustrating that. Just take a peek at the notes real quick. Okay, so same thing for the function f of x equals x. Use a regular partition of the interval a, b, take c sub k equal to x sub k, so they told us to do that this time, to prove that the integral from a to b of x dx is b squared over 2 minus a squared over 2. All right. We'll take the integrand to be the function x. X is a continuous function, as in the previous one. Theorem 5.1 tells you this thing is integrable. So if we'll take any partition It has a norm approaching 0, like a regular partition. That's a way to evaluate the integral. So do as we did before. Regular partition, take all the delta x's to be the same, b minus a over n. X sub k is a plus k, b minus a over n. C sub k, this time, choose it to be x sub k. So now I need a formula for the c sub k's. And we get, choosing c sub k to equal x sub k, we get this for the c sub k's. So the algebra on this one's going to be a little bit longer. All right. So as before, if n approaches infinity, then the norm of the partition approaches 0. The norm was b minus a over n. N goes to infinity, b minus a over n goes to 0 as needed. We're good. So the integral from a to b of x dx is the limit of the Riemann sums. As before, in fact, this is the same statement we had in the previous one. This time, f of c sub k, f of x equals x. It's the identity function. So we plug c sub k in, we get c sub k out. So now we just need to evaluate this limit. C sub k, c sub k has a bit more involved expression for c sub k than we had before. Last time it was a constant. Here's what we get for c sub k. All right, so we'll plug in for c sub k, the expression for it. C sub k will always look like this if we use right-hand endpoints in a regular partition. So we'll get this, and now we simply need to do the summation and the limit stuff. We're summing from k equals 1 to n. That's the only k that I see. All the other stuff is independent of k. So this is the only thing affected very directly by the summation. All right, we've got a b minus a over n. No k's there. We can bring that outside of the summation. That's distribution backwards. It's factoring. And then we've got a sum of the a's and a sum of this stuff here. Sum from 1 to n of a, sum from 1 to n of this stuff here. K equals 1 to n. I can bring the b minus a over n, this b minus a over n, out in front of that summation. As long as it ain't got k's in it, it can come outside of the sums. As long as it doesn't have n's in it, it can come out of the limits. We got some n's here, so this has an n in it, so it can't come all the way out front, of course. All right, now we're in business because we know how to sum some things. We stated these formulas in the last section, wasn't it? Sum from 1 to n of a, that's a plus a plus a, n times, so that's just n times a. Sum from 1 to n of k, the sum of the first n natural numbers. We had a formula for it. In fact, here is that formula. So we'll replace this summation with this equality, this quantity. And now it's a matter of cleaning up the algebra and evaluating the limit. All right. Let's distribute this b minus a over n over these two terms. Let's see, the n's will cancel this first time, and we'll have a times b minus a times b minus a. Here we'll get a b minus a over n squared, get that thing squared, and the summation result given here. Okay, let's do a little bit more algebra before we evaluate the limit. Get the n's all together in one spot. So here's what we had on the last line. This is a constant with respect to n. So the limit, I just deal with that as a constant. Then we've got a limit as n approaches infinity of this second stuff. We got well, here's a constant, b minus a squared we can bring out front. I've got a 1 over n squared. So I can't bring that outside of a limit when n changes. So we're left with that 1 over n squared inside. Let's put it in the denominator here. There it is. So the books are balanced in this one. We've taken the limit and pulled all the constants out that we can, leaving us with this limit. All right, if we distribute here, we get n squared plus n. We then have a limit as n approaches infinity of n squared plus n over 2n squared. We have a technique for dealing with such limits. Let's divide numerator and denominator by the highest power of the variable in the denominator. So that'd be n squared. Divide numerator and denominator by n squared. That is, multiply by 1 over n squared over itself. Distribute and simplify. N squared over n squared is 1. 2n squared over n squared is 2. n over n squared is 1 over n. So that's the only one with n's in it. Use the limit properties for quotients and sums. We ultimately end up considering this particular limit here. You'll always have 1 over n's in it if you approach it this way, and that you know is 0. So that limit here, we're evaluating the limit. We get a 0 there. We get it ultimately, we had it really isolated, the evaluation of the limit. So we pick up a 0 there. We've got, let's see, distributing, we have BA minus A squared, AB minus A squared, say. B minus A squared times a half, B minus A squared, B squared minus 2AB plus A squared over 2. And let's see, here's an AB. Here, when I cancel the 2's, is a negative AB. So the AB's terms are gone. We're left with B squared over 2 minus A squared plus A squared over 2 from this part here, leaving us with a negative A squared over 2. And that's what we were supposed to get. So the integral from A to B of x dx is B squared over 2 minus A squared over 2. Odd sounding things to have. For the values of these, there's a pattern. If you've seen integration before, you're not in the least bit surprised by these. Let's do another one. All right, let's look at x squared. Use a regular partition of the interval from A to B. Take c sub k equal to x sub k like we just did to prove the integral from A to B of x squared equals b cubed over 3 minus a cubed over 3. With what we saw in the previous one, and even more glaring in this one, you know, this reminds me, there's a relationship between x squared and cubing over 3. That relationship is antiderivatives. The fact that an antiderivative of x squared is 1/3 x cubed, and we're getting 1/3 things cubed here, that ain't a coincidence. If you've seen this before, you recognize it. If you haven't, it still should catch your eye that it seems like something's going on with antiderivatives. As far as the teaching thing goes, it's just a coincidence at this stage. But in the next section, we'll use antiderivatives to evaluate definite integrals in a thing called the fundamental theorem of calculus. So it must be a big deal. But this is all we have for now. So this is what we're going to have to do for now. Okay, so the question is, do what you just did for the x function, now for the x squared function. All right, well, f of x equals x squared is continuous and so integrable. So if we pick a partition, the norm of which goes to 0, and we do our thing with Riemann sums and limits, that'll give us the value of the integral. Knowing that the value exists allows us to approach it this way. Note 5.3.8. All right, so we'll take a regular partition. Delta x, or delta x sub k, will be b minus a over n. X sub k will be as we had before. We're choosing c sub k to be x sub k to be what we had before. So very similar to the previous one. As n approaches infinity, the norm of the partition will approach 0, as in the previous 2 examples. So the integral from a to b of x squared dx, limit of the Riemann sums. We had exactly this term in the previous 2 cases. The only difference here is f does something different to c sub k. It squares it this time. So f of c sub k squared. B minus a over n will sum and then take a limit. We have an expression for c sub k. Here it is right here. So next page, next slide. We'll substitute for c sub k its representation. Okay, this time it gets squared. So more algebra to do this time. All right. We could take the b minus a over n. We could bring that out front of the summation because there's no k's in it. We can't bring it out front of the limit because there are n's in it, and it's a limit as n changes. So we get this summation. This thing squared, first squared, a squared. Twice the product, 2ak times this quotient, 2ak times this quotient, plus the second one squared, last squared. K squared, b minus a over n squared. So we've taken care of the algebra and the squaring. Now Let's deal with the summations. We'll have a sum from k equals 1 to n of a squared, constant. So we'll just get a squared plus a squared plus a squared n times. It's n a squared. Here we've got a 2 and an a and a b minus a over n. No k's. We bring those out front. Sum from 1 to n of k, and you know what that is. Here we've got a k squared, constants. Bring this out front of the sum and take a sum from 1 to n of k squared to produce this. We know what this is, and we know what this is in terms of the parameter n. We had the sum from 1 to n of k is n times n plus 1 over 2. Sum of k squared, this one we haven't used yet today, n times n plus 1 times 2n plus 1 over 6. Proofs of these things in one of the appendices. So we'll substitute for this sum, n times n plus 1 over 2. Substitute for this sum, the over 6 thing. And now we've got a limit as n approaches infinity of this stuff here. All right. We'll deal with properties of limits, and your concern is the ends. All right. Here's where we left off on the previous slide. So let's see. Let's take this b minus a over n. If I multiply it by this term, the ends will cancel. We'll pick up just an a squared here. There's the a squared. Let's take this n to the next term. That'll give us an n squared in the denominator. Take this over n to the next term. That'll give us an n squared and another n cubed in the denominator. I've taken the b minus a and written it as squared in the numerator. So the books balance. This equals the previous thing. And how about we, let's take this n squared and put it in the denominator of the numerator. I'm trying to get the n's together. So let's write this division by n squared is multiplication by 1 over n squared in the numerator. So we get an n times n plus 1 is n squared plus n. So let's distribute on that, divided by n squared. Here we've got an n cubed. Let's do the same thing in this. There's the n cubed. If you'll multiply this out, FOIL, and then distribute the n, you'll get this term, which is also cubed, 2n cubed and some other terms. Now we're ready to take the limits, or maybe we'll do a little bit of simplification first. I can take this n squared, divide it into these two terms, take this n cubed, divide it into those 3 terms. Let's do that. So that's what's written here. N squared over n squared is 1. N over n squared is 1 over n. Deal with the n cubed, it'll produce a 2, a 3 over n, and a 1 over n squared. There you go. Now let's deal with the limits. Okay, everything's a constant except for these things with the n's in them. So use your properties of limits, ultimately, to get the limit on the 1 over n terms. Everything else is constant. We get a limit as n approaches infinity, 1 over n from that one. We get a 3 times a limit of 1 over n as n approaches infinity there. Let me bring the 3 out front. Here we've got a limit as n approaches infinity, 1 over n squared. So take the squaring outside to produce this. And maybe you don't know much about limits as things approach infinity, but I know this, 1 over n approaches 0. So this will go to 0, this will go to 0 times 3. This will go to 0 squared. So I've very much isolated just the limits of 1 over n, as we've often done. So evaluating those limits, we pick up the zeros, simplifying the arithmetic. The following algebra is correct. I leave it to you to pause the video and read through it in detail if you so desire. But the algebra is correct and not complicated, a little tedious, but simplifies down to b cubed over 3 minus a cubed over 3 like it was supposed to. So to integrate x squared from a to b, we get this quantity here. That's all we know, though I got some pretty good circumstantial evidence that this has something to do with antiderivatives. You don't know that yet. You won't know that until we state the fundamental theorem of calculus. All right, so we know some ways to integrate very special functions, constant functions, the identity function, x, and the x squared function. And I guess combinations of those, because we had some properties for definite integrals we stated earlier. I could integrate any second degree polynomial with the information we have. Here in number 36, they've said, evaluate the integral from 0 to pi halves of theta squared d theta. Okay, well, it's a squaring function, and we just had a quickie little formula, equation 4, it was that exercise we just did, that tells us you want to integrate from 0 to pi halves of theta squared. Simply take the upper bound cubed over 3 minus the lower bound cubed over 3, where the upper bound is pi halves and the lower bound is 0. Plugging in, a equals 0, b equals pi halves, produces pi halves cubed over 3 minus 0 cubed over 3, pi halves and 0 plugged in. So give us pi cubed over 8 times 3, pi cubed over 24 minus 0. So piece of cake once we have the little rule on how to evaluate these. So we don't need to go through that limit stuff for a squaring function anymore. Back to the notes, where we formally define, right, and this, it's all been leading up to this idea. We formally define areas under curves for non-negative functions as integrals. So if y equals f of x is a non-negative and integrable function over the closed interval from a to b, the area under the curve y equals f of x from x equals a to x equals b on the interval from a to b is the integral of f from a to b. The area is the integral from a to b of f of x dx. It's a definition of area. You can't argue with it because it's a definition, but we set all this integral stuff up to give us exactly that, to give us areas under curves. Let's look at number 18, which actually has us use an area formula to evaluate an integral. So we now know areas and integrals are the same thing by definition. Graph the integrand and use known area formulas to evaluate the integral. Integral from -4 to 0, 16 minus x squared square root of dx. So it must be that we know the area under this curve. It says use known area formulas. Well, let's see what we got. Let's take y equals to 16 minus x squared square root of the integrand. You recognize that? How about we square both sides? If we square both sides, we get y squared equals the square root of 16 minus x squared squared, or 16 minus x squared. When we don't entirely have y squared equals 16 minus x squared, notice if y equals the square root of something, then y can't be negative. Square roots are never negative. Remember that story from back when. The square root symbol means take the non-negative square root. So y itself must be non-negative, must be greater than or equal to 0. This little equation doesn't reflect that, so I have to add that on as a caveat on the side. We've lost the sign of y when we did the squaring. When you solve equations and you square both sides, you worry about extraneous roots. That's called in pre-calculus. So we've got a similar concern here. Notice y is greater than or equal to 0 is part of the story, as well as the relationship y squared equals 16 minus x squared. If we'll rearrange that, we get x squared plus y squared equals 16, and y is greater than or equal to 0. That I recognize. That's the equation of a circle with center 0 and radius square root of 16, radius 4. So what we get for the graph of y equals 16 minus x squared square root of is a circle of radius 4 and center at the origin with the added condition that y is greater than or equal to 0. Actually, we don't get the circle, we get the semicircle. So we get this semicircle. All right, that's the graph of the integrand. They've asked us for an integral from -4 to 0. According to the definition we just had, that would be the area under this curve between here and here. Let's draw a picture of that. It'd be this area here. Can you find, is this 1/4 the area of a circle of radius 4? Sure, you can find that. You got your pi r squared thing going on for the area of a circle. So the function itself is non-negative, it's a square root. So by definition, This integral represents that yellow area. Can you find that yellow area? Notice integral from -4 to 0, looking along the x-axis. X ranges from -4 to 0. So we need to find that area. No problem. Pi r squared over 4. So we get pi r squared over 4 evaluated at, if you can read it at the bottom, evaluated at r equals 4. The radius is 4. So that gives us pi 4 squared over 4. That'd be 16 pi over 4, or 4 pi. So on the rare occasion that we know the area, then we can use areas to find values of definite integrals that represent areas at least. And what do you know the areas of? Not much. Circles. That's probably about it, other than flat things, triangles and rectangles and stuff. Circle is the only thing I can think that you might know the area of as a more fundamental formula, the pi r squared deal. Let's see, we need more from the notes. What else we got? Average value. All right, if f is an integrable function on AB, then its average or mean value over that interval, average value of f, is defined to be 1 over b minus a, integral from a to b of f of x dx. We hinted at this earlier, but we didn't have a way to actually evaluate those areas under the curve earlier. We had ways to approximate them. Now we've got, at least for some special cases, and soon for a lot more things, we've got ways to find those integrals. So average value is defined to be this. Let's look at 3 more examples, some of which will illustrate average values. Number 62, graph the function h of x equals negative absolute value of x, and find the average value over the intervals -1 to 0, 0 to 1, and -1 to 1. And whoops, I must have a typo there. Let's take h of x equals positive absolute value of x. I believe I got a typo there. So we can treat it as these particular areas here. All right, with the absolute value function, not the negative absolute value function, we get the following typo. I will fix that in the posted notes online. And let's find the averages. All right, by definition, the average is 1 over b minus a times the integral from a to b of h of x dx. If it's a non-negative function, then I can totally talk areas as representing integrals. They want the average of h over the interval -1 to 0. Okay, so we'll have 1 over b minus a. Here's b, here's a. We'll have 1 over b minus a, 0 minus -1, so just 1. In the integral from -1 to 0, -1 to 0, that would be this little yellow area here. That's, let's see, it's 1 unit wide, 1 unit tall. The square would have area 1. We cut it in half with a diagonal, and we get an area of a half. So the integral is a half. This coefficient is 1. The average value is 1 times a half, or 1/2, which makes perfect sense. And it's above 1/2 about half of the time, and below 1/2, well, exactly half of the time. And by definition, we get the value as a half, but that looks fairly reasonable for a function that ranges from 0 to 1 in a very uniform way. That makes sense that the average would be 1/2. All these are going to be 1/2, it turns out. How about on the interval 0 to 1? Well, okay, from 0 to 1, we'll look at this picture. It's the same area. A and B changed. We'll have 1 over b minus a. B is 1, a is 0. So 1 over 1 minus 0 this time. Also a coefficient of 1. The integral represents the area. It's 1 by 1. It's a 1 by 1 square that's been cut in half. A half is the value of the integral, and so 1 times a half is the average value of the function. On the interval from -1 to 1, all right, a is -1, b is 1, so we'll have 1 minus -1, b minus a. The area now, this area is a half plus this area, total area under the curve, so 1/2 plus 1/2. The total area is 1. The coefficient is 1 over 1 minus -1. The coefficient's a half, and the value of the area is 1. So these interchanged in this last one, but the average value is still a half, which makes a very reasonable sense looking at the graph of the function. So average values computed using integrals. And here we're computing integrals using areas and graphs of functions. Show that, number 76, the value of the integral from 0 to 1 of the square root of x plus 8 dx lies between these two numbers here. Okay, this time we got a little more complicated problem because we don't know what to do with the square root of x plus 8. I can maybe find max and min values of it, but we don't know how to deal with this. I mean, we could take partitions and go at it. I think the square root would blow everything up, and the techniques we know won't work. But let f of x be the square root of x plus 8, x plus 8 to the 1/2. And let's find the maxes and the mins of the integrand on the interval 0 to 1. I'm looking for the minimum of f and the maximum of f in some things we stated previously. So we'll take the derivative, bring the exponent out front, subtract 1 from the exponent, use the chain rule, multiply by the derivative inside, which is 1, so it's omitted. And we get 1 over square root of x plus 8. Actually, I've dropped a 2 here, it looks like. Another typo, dropped a 2 here from this. We get 1 over 2 times the square root of x plus 8. But nonetheless, there's no critical points except -8. We've got a continuous function on the interval 0, 1. The only critical point is -8, and that's not in this interval 0, 1. So the function must have its max and min at the endpoints. Remember, extreme values for functions on closed intervals, check the endpoints and the critical points in that interval. The endpoints are 0 and 1. There are no critical points in that interval. -8 counts as a critical point, but it's not in this interval. So all we have to do is check the endpoints. At 0, the function takes on the value 2 on the square root of 2. And at 1, the function takes on the value square root of 9 or 3. So we know then this must be the minimum of the function, and this must be the maximum of the function. Min f is 2 on the square root of 2, and max f, another typo, max f is 3. So this is the largest, this is the smallest. We know that by properties of continuous functions on closed and bounded intervals as we started chapter 4. Okay, we've got a minimum and a maximum. We had the max-min inequality theorem for integrals that said the minimum of a function times the interval on which we're integrating is less than or equal to the integral itself, and that's less than or equal to the maximum of the function times b minus a. Here, we saw the minimum was 2 on the square root of 2. The interval is 0 to 1. So a is 0, b is 1, b minus a, 1 minus 0. So we just get a 1 there. And we get 2 on the square root of 2 is less than or equal to the value of the integral. Here's the integral written with the function f, and that's less than or equal to the maximum. And we saw on the previous slide the maximum was 3. B minus a is still 1 minus 0. That is, we've got 2 on the square root of 2 less than or equal to the integral they gave us, less than or equal to 3 over here on the right. And that's what they ask us to show. 2 on the square root of 2 is less than or equal to, the integral is less than or equal to 3. So if I can find maxes and mins, I can put bounds on what the integral is. Tell me anything else about this integral? Not much. It's a non-negative function. It has an area interpretation. It's an area under a parabola or something like that. So we're pretty much stuck on this one until we know more about how to evaluate integrals. Turns out it's not hard to evaluate this integral. We just don't have the equipment to do so just yet. We will before Calculus 1 is over. Another somewhat more exotic average value function, it's told as a word problem, says if you average 30 miles per hour on a 150-mile trip, and then you return over the same 150 miles at the rate of 50 miles per hour, what is your average speed for the trip? Give reasons for your answer. All right, so naively, you might think, now you went 30 miles an hour part of the time, 50 miles an hour another part of the time, must average 40 miles per hour, the average of those two. Well, no, that ain't gonna work because you went 30 miles an hour a lot longer than the amount of time you drove 50 miles an hour. You didn't do these evenly. And that's why the answer is not 40 very informally. Let's formalize it with calculus. So they're asking for average of something. All right, let's define a function f that represents speed, and we'll find the average of that speed function over the relevant time period. So define the function f of t as your speed as a function of time t, where t is measured in hours and f is measured in miles per hour. It's a speed. So we've got f defined piecewise as f of t is 30 miles per hour for t between 0 hours and 5 hours. It took 5 hours to drive this 150 miles at 30 miles per hour. And f of t is 50 miles per hour between t equals 5 hours and 8 hours. You turned around and came back. You traveled 150 miles, 50 miles an hour. That's going to take a total of 3 hours. So it's a weighted average is what you're finding here, but we'll do it in terms of integrals and areas. So we get f of t, the speed function, defined piecewise as 30 miles per hour for t between 0 and 5, and 50 miles per hour between 5 and 8. We want to find the average of that function over the time period 0 to 8. So a is 0, b is 8. There's the piecewise defined function. By the definition of average speed, we'll have, average of a function, we'll have average of f is 1 over b minus a times the integral. We're looking at the interval from 0 to 8. So we'll have 8 minus 0, the length of the interval, that's the 8 hours. And we'll integrate the speed function, f of t dt. By additivity, we can break that integral from 0 to 8 into an integral from 0 to 5 plus an integral from 5 to 8. What does the f of t function look like? Well, sometimes it's 30 and sometimes it's 50. And here's those specific times when it takes those values on. So we'll break the integral up. Then we need to integrate the 30 part and integrate the 50 part. Do you know how to integrate a constant function? I do now, because we showed that here in one of the examples earlier today in this video. So we'll have 30 times b minus a, the constant c times b minus a is what we've got. So we have constant times 5 minus 0, 50 times b minus a, constant times b minus a, b is 8, a is 5. So we get 1/8 of 30 times 5 is 150. 50 times 3 is also 150. Not a surprise with that. So we get 300 divided by 8. We get 75 over 2 miles per hour. That's what, 37.5 miles per hour. So if you naively guessed it would be the average of these two, that was a bit of an overestimate, because that's not what you average over. You average over time, and you spent more time driving slowly than you did driving quickly. That's why this is less than 40 miles per hour, also rather informally. Formally, there's how you find the answer. Treating it as a piecewise defined function and using the definition of average value. All right, so that takes care of 5.3. In 5.4, we'll do the fundamental theorem of calculus, and we'll have a more streamlined way to evaluate these integrals. I will see you there shortly. The lights at the end of the tunnel here with Calculus 1, and we'll do fundamental theorem of calculus next episode. Have a nice day. Bye-bye.